Every round thing you have ever held was made round by someone. A ball, a marble, a coin, each one was shaped on purpose, by a hand or a machine that meant to make the curve. Leave matter to itself down here, and it never rounds itself off. A broken rock stays jagged, a pile of sand stays a heap. On the human scale, roundness is the fingerprint of something deliberately made. But look up, and almost everything in the sky is a ball. The moon is a ball. The sun is a ball. Every planet, every star ever photographed is a sphere, and not one of them was shaped by anyone. Nothing told them to be round. They were built from lopsided collisions of jagged rubble, and they came out as near-perfect spheres anyway. The sun is round to within about 10 kilometers out of nearly 1,400,000, smoother than a marble from any factory. Something is quietly sculpting worlds into balls, everywhere, with no hands at all, and the shape it chooses is not decoration. It is a confession about a force you have lived with your whole life and never once questioned. Get comfortable. Hit subscribe if you're new here, because by the end of this, you will never look at the full moon or the ground beneath your own feet quite the same way again. Now, let's slowly ease into this. Part 1. The question hiding in plain sight. There is a question so ordinary that almost no one ever asks it out loud. You have been looking at the answer your entire life. Every time you have glanced up at the moon, every time you have seen a photograph of a planet, every time you have watched the sun sink slowly toward the horizon, the answer has been sitting right in front of you. And still the question underneath it tends to slide past, because the thing it asks about feels too familiar to need explaining. The question is this: why is everything in space round? Sit with that for a moment. The moon is a ball. The sun is a ball. Every planet in the solar system is a ball. Every star you have ever seen, every world that has ever been photographed by a spacecraft or resolved by a telescope is, to a very good approximation, a sphere, not a cube, not a pyramid, not a flat plate or a long splinter or a lumpy, irregular mass with corners and edges. A ball, the same shape, over and over, across an unthinkable number of objects, separated by distances the mind cannot really hold, made of different materials, formed at different times, in different corners of the universe. They all arrived at the same shape, and nobody told them to. That last part is the part worth slowing down on, because nothing about the raw materials of a world specifies a shape at all. A planet is not poured into a mould. It is not carved by a hand that prefers curves. A planet is assembled over millions of years out of collisions. It begins as dust and gravel and boulders and mountain-sized chunks of rock and metal and ice, all of it drifting in a disk around a young star, all of it crashing together in a slow, violent, entirely disorganized process. Nothing in that process cares about geometry. The pieces that come together are jagged and irregular. The impacts that build the world are lopsided and chaotic. If you were designing a machine to produce a specific shape, this is close to the last process you would choose. And yet, out the other end, again and again, comes a sphere. So somewhere between that chaotic pile of colliding rubble and the finished world, a decision gets made. A shape gets chosen. And the remarkable thing, the thing this entire conversation is built around, is that the choice is not really a choice at all. It is forced. There is a rule operating here, quietly, underneath the chaos, and the rule is strong enough that it does not matter what the pieces looked like when they started. Given enough material, the rule takes over, and the rule only ever produces one answer: round. You can feel how odd this is if you compare it to almost anything else in your experience. Look around the room you are in. Nothing in it made itself round by accident. The round things near you, a cup, a ball, a coin, a lens, were all shaped that way on purpose, by a person or a machine that intended the curve. The things that were left to form on their own, a pile of sand, a broken rock, a crumpled sheet of paper, a snapped branch, are lumpy and irregular and full of edges. On the human scale, roundness is a sign that something was deliberately made. Left alone, matter on the scale you live at does not round itself off. It stays jagged. To feel why the rule flips as you climb in size, you have to appreciate how staggeringly weak gravity actually is on the scale of your own life. Gravity feels powerful to us only because we happen to be pressed against an entire planet, but the force itself, considered piece by piece, is almost nothing at all. Consider that a small magnet, the kind you could hold between two fingers, can pluck a paperclip up off a table. That tiny magnet is winning a tug of war against the gravity of the entire Earth, all of its many thousands of billions of tons, pulling the other way. You defeat the gravity of the whole planet every time you lift a spoon to your mouth. On the scale of a rock, a house, a single mountain, gravity is a whisper, hopelessly outmatched by the ordinary strength of materials, by the stiffness of stone, and the bonds holding atoms to their neighbours. This is exactly why nothing the size of a person, or a building, or even a modest mountain ever rounds itself off. The gravity of a boulder is so faint that the boulder's own rock does not even feel it, and so the boulder keeps whatever jagged shape it was chipped into, essentially forever. Gravity has only one way to become important, and it is not to grow stronger for each piece of matter, because it cannot. It is to accumulate. It must gather material, more and more of it, piling mass upon mass until the sheer quantity of matter finally tips the balance against the strength of the rock. A pebble's gravity is nothing. A mountain's gravity is very nearly nothing. But keep stacking mass, keep piling it up past the scale of mountains and continents and small moons, and eventually the whisper swells into a voice, and then into a command that cannot be refused. But go up in size, far up, past mountains and past continents, up to the scale of whole worlds, and the rule flips completely. At that scale, roundness stops being the exception and becomes the law. At that scale, it is the lumpy, irregular objects that are rare and special, and the smooth spheres that are ordinary and expected. Something changes as you climb the ladder of size. Some force that is utterly negligible in your kitchen becomes, at the scale of a world, the single most important sculptor in the universe. That force is gravity, and the shape it likes, the only shape it ever produces when it is given a free hand, is the ball. Here is the thread I want to pull on for the next couple of hours, gently, one turn at a time. Roundness, out there, is not a decoration. It is not a coincidence, and it is not an aesthetic preference of the cosmos. It is a confession. When you look up and see that a world is round, you are looking at direct, physical evidence that the world's own gravity has grown strong enough to overwhelm the strength of the rock and metal and ice it is built from. The sphere is what gravity builds when nothing is left to stop it. Every round thing overhead is a place where gravity won, and once you understand that, the sky reorganizes itself a little. The roundness stops being wallpaper and starts being information. The fact that the moon is round tells you something specific about the moon. The fact that a tiny asteroid is not round tells you something specific about the asteroid. The exact way a planet is round, the subtle way it bulges or leans away from a perfect ball, turns out to carry a fingerprint of how fast it spins, how strong its material is, and even what it was like when it was young. Shape becomes a language, and the first word in that language, the one every large world in the universe says, is the sphere. There is a reason this question is worth 2 hours of your evening rather than 2 minutes. It is because the answer does not stay simple. It starts simple, with a single force and a single shape, and then it keeps opening. It opens into the question of exactly how big a thing has to be before gravity wins, and why some moons cross that line while others, larger, do not. It opens into the strange truth that nothing in space is actually a perfect sphere, that spin quietly ruins the shape, and that the amount of ruin is itself a measurement you can read. It opens into the roundest object anyone has ever measured, which is not a planet at all. It opens into the tallest mountain that physics will ever allow to exist, anywhere, a number written directly into the rock by gravity. And it opens, at the far end, into a genuine puzzle, because the same force that so patiently rounds off every world refuses to round off the universe as a whole. The largest structures in the cosmos are not balls. They are threads and walls and immense, ragged webs. So the ball, it turns out, is gravity's favourite shape, only across a particular band of sizes. And figuring out where that band begins and ends tells you something about gravity itself that physics is still, to this day, working to fully understand. For now, though, hold on to the simple version, because everything else is built on top of it. Look up at anything round in the sky and read it as a sentence. This object is large enough that its own weight defeated its own strength. This object fell inward on itself until there was nowhere lower left to fall. This object is round because, at its size, being anything else was not allowed. That is the confession hidden in plain sight, in the most ordinary shape in the universe. And the first thing we need to understand, before we can understand anything else about it, is why the shape that gravity chooses, out of every shape it could possibly choose, is a ball. Part 2. The shape with no corners. Before we can talk about why gravity makes worlds round, we have to be precise about what a sphere actually is, because the definition itself is the whole secret. A sphere is the set of all points that sit at exactly the same distance from a single centre. That is the entire idea. Pick a point in space, call it the centre, choose a distance, and then mark every location that sits that far from the centre, in every direction at once. What you get is a perfect ball. Every spot on its surface is precisely as far from the middle as every other spot. There are no closer places and no farther places. There is no highest point and no lowest point. A sphere is, in a very exact sense, the shape that treats every direction the same. That last property is the one to hold on to, because it is exactly the property that gravity is trying to produce. Gravity, stripped down to its simplest behaviour, does only one thing. It pulls matter toward matter. Every scrap of material in a body pulls on every other scrap, and when you add all of those pulls together across a whole world, they point, on average, toward one place. That place is the centre of mass, the balance point of the entire object. And the instruction gravity gives to every piece of the world is always the same monotonous command. Move toward the centre, get closer to the middle, come down. Now think about what that instruction does to a shape over time. Imagine a world that starts out lumpy, with a tall ridge sticking up on one side and a wide plain on the other. Every particle in that tall ridge is being pulled toward the centre of the world, which means the ridge is, in the most literal sense, being pulled downhill. It is higher than it needs to be. It has somewhere lower to go. Gravity keeps tugging on it, and if the material is able to move at all, it will eventually give way, and the high place will slump down toward the level of everything else. Meanwhile, any dent or hollow, any place that sits too low, tends to get filled in as material flows toward the middle from all sides and piles up. High places come down, low places fill in. And the process does not stop until there are no more high places and no more low places left, until every point on the surface sits at the same distance from the centre as every other point. That final, settled shape, the one with nowhere left to fall, is the sphere. This is why the sphere is not just one option among many for gravity. It is the finish line. It is the shape you are guaranteed to end up with if gravity is allowed to keep rearranging material until it can no longer find anything that is higher than anything else. Physicists have a more formal way of saying this, and it is worth hearing because it makes the inevitability clear. Of all the possible shapes you could make out of a fixed amount of material, the sphere is the one that packs that material as closely as possible around its own center. It is the most compact arrangement there is. It has the smallest possible surface for the volume it contains, and it sits at the lowest possible gravitational energy. Any other shape, any bump, any elongation, any flattening, holds some of its material farther from the center than it needs to be, which means that material is holding extra energy, sitting higher than it has to, waiting for a chance to come down. The sphere is the shape where all of that has already happened. It is the bottom of the hill for an entire world. There is a comparison that makes this feel less abstract, and you have watched it happen 1,000 times without thinking about it. Consider a single drop of water hanging from a tap, or a bead of water rolling across a waxed surface, or a droplet floating in the weightlessness of a space station. It pulls itself into a ball, not because water knows any geometry, but because the surface of the water is being pulled tight by a force, and the shape that satisfies that pull most completely, the shape with the least surface area for the volume, is the sphere. In the case of the water drop, the force doing the pulling is surface tension, the tendency of the liquid surface to shrink itself as small as it can. In the case of a planet, the force is gravity. These are two completely different forces, operating for completely different reasons, at completely different scales, and yet they produce the same shape, because they are both solving the same underlying problem. Both are looking for the most compact arrangement of a fixed amount of stuff, and the answer to that problem, every single time, is a ball. So when you look at a water droplet and then look at the full moon, you are looking at the same piece of geometry answered by two different forces. The droplet is round because surface tension pulled it into the tightest shape available. The moon is round because gravity did. The scales could not be more different. A droplet is a few millimeters across and rounds itself in a fraction of a second. The moon is more than 3,400 kilometers across and took ages to settle. But the logic underneath is identical, and it is the logic of a force with a single preference, applied without exception to every part of an object, until the object has no way left to disobey. It helps to make this concrete with a shape that could not be more different from a ball. Picture trying to build a cube-shaped planet, an enormous stone die, thousands of kilometers on each side, hanging in space. Suppose you somehow manage to assemble it that way, with 8 sharp corners and 12 straight edges and 6 flat faces. It would not stay a cube for a single moment in geological terms, and the reason is a direct consequence of what gravity is trying to do. The corners of that cube are the points that stick out farthest from the center. They are, in the most literal sense, the highest places on the whole body, the parts holding the most gravitational energy, the parts with the farthest to fall. Gravity would pull those corners inward with everything it had. The material there, unable to bear being held so far above the level of everything else, would crumble and slump and flow toward the center. The corners would collapse first, then the edges, then the faces would bulge outward to fill the gaps, and the whole enormous die would settle, over time, into the one shape where no corner sticks out and no face caves in, the shape where every point on the surface has fallen as far as it possibly can. It would become a ball. You cannot build a large cube in space and keep it, because a large cube is nothing but a sphere with a great deal of extra energy stored in its corners, waiting for gravity to spend it. The same is true of a pyramid, a cylinder, a slab, or any other shape you might try. Every one of them has high places, and gravity always finds the high places. There is a useful picture that physicists carry for this. Think of every possible shape a world could take as a position on a rolling countryside of energy, with the low valleys being the low-energy shapes and the high peaks being the high-energy ones. A jagged, cornered, irregular body sits high on a slope of that terrain, and it will always tend to slide downhill toward lower energy if it possibly can. The sphere sits at the very bottom of the valley. It is the lowest energy shape there is, the one resting place from which there is no further downhill to go. Gravity is simply the tendency of a massive body to roll down that slope, and the sphere is the floor of the valley where the rolling finally stops. This gives us our first real handle on the whole mystery, and it is worth stating as plainly as possible, because we are going to keep coming back to it. A sphere is what gravity builds when nothing is left to stop it. That is the sentence at the bottom of everything else in this story. Gravity always pulls toward the center. Given the freedom to rearrange material, it will keep pulling high places down until nothing is high anymore, and the shape that remains is the ball. The only question then, the question that everything else in this story turns on, is that little phrase at the end, when nothing is left to stop it. Because something can stop it. Gravity does not always get its way. There is a competitor, a force pushing back, holding shapes together against gravity's endless downhill pull, and whether a world ends up round or ragged comes down entirely to which of those two forces is winning. So before we can understand the round worlds, we have to meet the ones that got away, the lumpy ones, the potatoes, the objects where gravity tried to make a ball and simply was not strong enough. Because the line between the potatoes and the planets is where this whole story really begins. Part 3. The potato line. If gravity always pulls toward the center, and the sphere is always the shape it is trying to build, then here is a fair question. Why is not everything in space round? Because it is not. For every smooth, ball-shaped world out there, the solar system is littered with objects that look nothing like a ball. They look like potatoes. They look like peanuts, like dog bones, like rubber ducks, like piles of gravel loosely stuck together. Go and look at the photographs that spacecraft have taken of small asteroids and comets and the little moons of the outer planets, and you will see some of the least round objects imaginable. Lumpy, cratered, irregular, covered in ridges and hollows, with no discernible center and no smoothness anywhere. If gravity is such a relentless sculptor, how did these things escape it? The answer is that gravity has a rival, and on small objects, the rival wins. That rival is the plain structural strength of the material the object is made of. Rock is strong, it holds itself up, it resists being pushed around. Ice, out in the cold of the outer solar system, is strong too, hard as stone at those temperatures. When you pile up a modest amount of rock or ice, the material at the bottom is perfectly capable of bearing the weight of the material on top without crushing or flowing or giving way. The mountain, or the ridge, or the lopsided lump just sits there. Gravity is pulling on it, exactly as it pulls on everything, tugging every high place toward the center. But the pull on a small object is feeble. The whole body barely weighs anything in the gravitational sense, so the downhill tug on any given ridge is gentle, and the strength of the rock easily withstands it. The high places do not come down. The shape does not settle. The object keeps whatever lumpy form it was born with, more or less forever. This is the balance at the center of the entire story, and it comes down to a contest between two things that both grow with size, but do not grow at the same rate. On one side is gravity, the pull that wants to round the object off. On the other side is material strength, the stubbornness that wants to preserve whatever shape already exists. For a small body, strength is overwhelmingly stronger, and the object stays a potato. But gravity has a crucial advantage in the long run, because gravity grows faster with size than strength does. As you make an object bigger, you add more mass, and more mass means more gravitational pull, and the pull piles up quickly. Double the size of a world, and its gravity does not just double. The weight pressing down at its center climbs far faster than that. Material strength, meanwhile, is more or less a fixed property of the rock. Rock is only so strong, no matter how much of it you stack up. So there is a size, a threshold, where the two lines cross. Below it, strength wins, and you get a potato. Above it, gravity wins, and you get a ball. Where is that line? For bodies made mostly of rock, the crossover happens somewhere around 600 kilometers across. For bodies made mostly of ice, which is weaker and gives way more easily, the line sits lower, closer to 400 kilometers. Astronomers sometimes call this rough cutoff the potato radius, which is exactly as charming and exactly as literal as it sounds. Below the potato radius, an object is likely to be a potato. Above it, the object has probably been pulled into a ball. And the wonderful thing about the solar system is that it hands us objects sitting right on both sides of that line, so we can watch the rule switch on. Consider Mimas, one of the moons of Saturn. Mimas is small, only about 396 kilometers across, and it is famous for an enormous crater that makes it look uncannily like a certain space station from the movies. But the thing to notice about Mimas is that, despite its modest size, it is round. It sits just above the line for an icy body, and gravity, just barely, has won. Now consider Proteus, a moon of Neptune. Proteus is larger than Mimas, about 420 kilometers across, and by the simple logic of size, you might expect it to be even rounder. It is not. Proteus is distinctly lumpy, an irregular, angular chunk with flat faces and blunt corners. Here are two icy moons, one smaller and round, one larger and not, sitting on opposite sides of the outcome, even though their sizes nearly overlap. The line is real, but it is not a razor's edge. It is a fuzzy zone where other factors, how cold the body is, what exactly it is made of, whether it was ever warmed and softened in its past, tip the balance one way or the other. The potato radius is less a wall and more a border region, and Mimas and Proteus are two travellers who ended up on different sides of it. The asteroid belt tells the same story even more starkly. Vesta, one of the largest asteroids, is about 525 kilometers across, and it is close to round, but not quite. An immense impact near its south pole punched out a basin so large it left the whole body slightly misshapen, a world that got most of the way to a sphere and then took a blow it could not fully recover from. Ceres, the largest object in the asteroid belt, at about 940 kilometers across, is comfortably above the line, and it is genuinely round enough that it has been promoted to the status of a dwarf planet. And below these, down among the ordinary asteroids and comets, the potato reigns. Comet 67P, which a spacecraft visited and orbited a decade ago, is shaped like a rubber duck. Two lumps joined by a narrow neck, only about 4 kilometers across. The asteroids Bennu and Ryugu, each less than a kilometer wide, look like spinning tops or cut diamonds. The little moons of Mars, Phobos, and Deimos are cratered potatoes barely 20 kilometers across. None of these objects is remotely round, and now you know precisely why. They are all far below the potato line. Gravity tried, and on objects that small, gravity simply is not strong enough to beat the rock. The fuzziness of that threshold is worth dwelling on, because it is where the physics gets subtle and honest. The potato radius is not a sharp wall with potatoes on one side and perfect balls on the other. It is a broad, blurry border zone, and exactly where a given body falls within it depends on more than size alone. It depends on what the body is made of, because ice is weaker than rock and gives way to gravity more readily, which is why icy bodies round off at smaller sizes than rocky ones. It depends on temperature, because a warm body is softer and flows more easily than a cold, brittle one. And above all, it depends on history, on whether the body was ever heated enough in its past to soften and settle, because a body that was once warm and mobile could have rounded itself long ago and then frozen that shape in place, while a body of the same size that stayed cold and rigid its whole life never got the chance. Two objects of identical size can end up on opposite sides of the line simply because one had a warmer youth than the other. This is why the small worlds of the solar system are such a menagerie of half-finished shapes. Saturn's moon Hyperion, some 270 kilometers across, is so porous and battered that it looks like a sponge, riddled with holes, tumbling end over end, so erratically that it does not even hold a steady rotation. The distant object called Arrokoth, visited by a spacecraft out past Neptune, is a contact binary, two separate lumps that drifted together so gently that they simply stuck like two snowballs pressed lightly against each other, never massive enough for gravity to merge them into a ball. Many small asteroids are not even solid bodies at all. They are rubble piles, loose heaps of gravel and boulders, held together by almost nothing, by their own feeble gravity and a faint stickiness between grains, one good bump away from scattering. None of these objects has enough mass for gravity to impose its will, so each of them keeps the accidental, particular, lopsided shape that its own past handed it. They are the unfinished drafts, the worlds that never cross the line, the places where the sculptor picked up the clay and then set it down again because there was not enough of it to work with. Imagine, for a moment, standing on the surface of one of these small worlds, a lumpy asteroid a few tens of kilometers across, a city-sized mountain of rock and metal tumbling slowly through space. The first thing you would notice is that down barely means anything. On the world you know, down is a firm, single, reliable direction, the same everywhere you go. On the asteroid, the pull beneath your feet is so faint that a careless jump could send you drifting off the surface entirely, up and away, slow enough to count the seconds as you rise. And down does not even stay put. Walk a few hundred meters across the lumpy terrain, and the direction the ground pulls you shifts, tilts, because you are near a body too small and too irregular to have organized itself around a single clean center. Boulders sit perched at angles that would be impossible on Earth, balanced on slopes that do not feel like slopes. The horizon is jagged and close and wrong, curving and jutting in ways that make no sense to an eye trained on a round world. You are standing in a place where gravity exists, but has not won, where the ancient contest between the pull toward the center and the strength of the rock is still, after billions of years, a stalemate. A potato is just a world that never grew big enough to lose that fight, and that is the setup for everything that follows, because now the question sharpens. We know there is a line. We know that below it, objects stay ragged, and above it, they are forced into balls. But we have not yet watched the forcing actually happen. We have not seen what it looks like when a world crosses that threshold, when gravity finally overpowers the rock and drags an entire body, high places and all, down into a sphere. That process has a name, and it is the true engine underneath the roundness of every planet, every large moon, and every star. It is the moment a world stops being a pile of rubble and becomes, permanently, a ball. So let us watch a world round itself. Part 4. When a world rounds itself. To watch a world become round, you have to go back to the beginning, to the time when the world was not yet solid. Every large body in the solar system, including the one you are standing on, began its life hot. The process that builds a planet is a process of relentless collision, and collisions release energy. Every chunk of rock that falls into the growing world arrives carrying the speed of its fall, and when it lands, that speed becomes heat. Multiply that by billions of impacts over millions of years, Add the heat released by the squeezing of the world's own weight and by the decay of radioactive elements buried inside it, and the young world does not stay a cold pile of gravel. It melts. For a long stretch of its early life, a world large enough to matter is soft, molten or partly molten, glowing, capable of flowing, and a material that can flow cannot resist gravity. This is the moment gravity has been waiting for. Picture that young world 4.5 billion years ago, before it had a solid surface. It is a churning, half-liquid mass of infalling rubble and molten rock, still growing, still being pelted, still hot enough in places to run like thick syrup. Now every one of the rules from a moment ago comes into force at once. Gravity is pulling every part of that soft mass toward the center. The high places have no strength left to hold themselves up, because the material is molten and yields to the slightest sustained pull. So the high places sink. The material flows down and around and inward, seeking the lowest place it can find, the way water seeks its level in a bath. Over ages, in slow motion, the ragged, lopsided, irregular young world settles. Its bulges drain, its hollows fill, its surface creeps, everywhere, toward a single smooth curve on which no point is any higher than any other. You are watching a planet choose the shape it will keep for the rest of time. And the shape it chooses, because gravity is doing the choosing, is a ball. This is the process physicists call reaching hydrostatic equilibrium, and the name, once you unpack it, describes exactly what you just watched. Hydro refers to fluid, to the ability of the material to flow. Static means settled, at rest, no longer changing. Equilibrium means balance. A world in hydrostatic equilibrium is one that has flowed until it found its balance and then stopped, because there is nowhere left to flow to. At every point inside such a world, the inward pull of gravity is exactly matched by the outward push of the pressure beneath, the weight of everything above pressing down balanced against the resistance of everything below pushing back. When that balance is struck at every depth, the material has no reason to move anymore, and the shape locks in. And the shape that this balance always produces, for an isolated body with nothing else acting on it, is the sphere, because the sphere is the only shape where the surface everywhere sits at the same gravitational level. That phrase, the same gravitational level, is worth pausing on, because it connects this cosmic process to something you see every day. Physicists describe the settled surface of a fluid world as an equipotential surface, which is a technical way of saying a surface of constant gravitational energy, a surface where every point is, in gravity's accounting, exactly as low as every other. Water, being a fluid, always arranges its surface into exactly such a surface. That is what sea level is. When we say the sea is level, we are not saying it is flat in the sense of a tabletop. We are saying its surface follows a curve on which gravity has no more work to do, a curve where water has nowhere lower to flow. Sea level is a piece of the same equipotential shape that a molten planet settles into, made visible in liquid water. The ocean is not sitting on top of a round Earth by coincidence. The ocean is round for exactly the same reason the Earth is round. Both are fluids, or were, and both have flowed until their surfaces found the level that gravity allows and no lower. So a world becomes round when it is soft enough to flow and heavy enough that gravity can make it. And here is the part that gives the whole process its permanence. Once a large world has rounded itself while molten, it cools. The outer layers harden into solid rock. And now the round shape is frozen in place, locked into a body that is once again strong and stiff. The world can be pelted with new impacts, it can grow mountains, it can crack and shift, but the underlying shape, the great sphere established during its molten youth, is set. It will stay round for as long as it exists, because it became round at the one time in its history when gravity had a completely free hand, and then it kept the record. This is why, Even worlds that are now cold and solid, worlds that could not possibly flow today, are still round. They are wearing the shape they took when they were young and liquid, the shape gravity pressed into them before they hardened. There is a further layer to this balance worth uncovering, because it explains not just the overall shape of a world, but the way its surface goes on behaving long after the world has hardened. Inside a large body, at every depth, there is a contest between two things. Gravity pulls the material downward, and the pressure of everything beneath pushes upward, and these two must balance almost exactly, or the material simply moves until they do. That is what the phrase hydrostatic equilibrium really describes. A body where, at every level, the weight pressing down is precisely supported by the pressure pushing back. Near the surface, this balance is what keeps the overall shape a sphere. But it also governs how the land floats. The solid rock of a planet's outer shell rides on top of hotter, denser, slowly yielding material below, and over long stretches of time it floats on that material much the way a block of wood floats on water, settling until the weight it presses down with is matched by the buoyancy holding it up. This is why mountains have roots. A tall mountain range is not simply piled on top of a flat surface. It is more like an iceberg, with a great mass of lighter rock reaching down into the denser material beneath, holding the peaks up from below. Push a mountain higher, and it must also sink lower, seeking that balance, which is one more reason there is a firm ceiling on how tall the land can ever climb. And it is why the surface of the ocean, the thing we casually call sea level, is not a simple sphere either, but a gently uneven surface that rises very slightly over places where the rock below is denser and sags where it is lighter, tracing out the true shape of the planet's gravity rather than a textbook ball. Physicists and map makers have a name for that real, subtly rippled shape, the surface that water would settle into everywhere if it could flow freely across the whole globe. They call it the geoid, and it is the honest shape of the Earth, the equipotential surface made visible, the surface that says, here is where gravity has finished its work and the water has nowhere lower left to go. Every one of these facts, the floating continents, the rooted mountains, the faintly uneven sea, is the same rule we watched shape the molten young world, still quietly at work billions of years later, still balancing weight against pressure, still insisting that the surface follow the level gravity allows and no other. This gives us a cleaner and more powerful version of the sentence we started with. It is not just that a sphere is what gravity builds when nothing is left to stop it. It is that, given enough mass, everything surrenders its shape. That is the real rule. Pile up enough material, and no object, however jagged it began, however strong its rock, can hold its original form. The mass creates the gravity creates the heat and the pull, and sooner or later the body gives up whatever shape it had and accepts the one gravity assigns it. A small asteroid can resist forever. A world cannot. Cross the threshold, and your shape is no longer yours. It belongs to gravity. And the surrender, once it happens, is permanent, written into the body and kept long after it has gone cold and hard and still. We now understand the machine. We know the two forces, gravity and strength. We know the threshold where gravity takes over, and we know the process, the molten settling into a ball, by which the takeover actually happens. But understanding the machine is not the same as feeling what it means, because this same rule, the one that shapes molten worlds in the early solar system, is the rule that is holding you to the floor right now, and it has a consequence for you personally for the most basic sense you have of up and down that is stranger than it first appears. To see it, we have to turn the question around, away from the worlds and toward yourself, and ask what it actually means to live on the surface of a ball. Part 5. Down is not a direction. Here is something you know so deeply that you have probably never once questioned it. You know which way is down. It is the most reliable fact in your life. Down is where dropped things fall. Down is the direction of the floor, the ground, your feet. Down is fixed and obvious, and always there, the anchor that every other direction is measured against. Up is away from it, and sideways is across it. And the whole architecture of your sense of space is built on the certainty of down. And yet down, that most solid and dependable of directions, is not actually a direction in space at all. It is something much stranger, and the roundness of the world is what gives it away. Think about two people standing on opposite sides of the earth, one in a city in the north and one in a city far to the south, near the other side of the globe. Both of them, if you asked, would point confidently downward, toward their own feet, and both would be completely correct. But their two downs are pointing in nearly opposite directions in space. One person's down is the other person's up. If you drew an arrow through the ground from each of their feet, the two arrows would cross somewhere near the middle of the planet and continue on to point at opposite sides of the sky. There is no single direction in the universe that is down for both of them, and yet neither of them is wrong, and neither of them feels the slightest bit tilted. Each one feels perfectly upright, perfectly normal, standing straight up with the ground firmly below. How can down be so certain for each person and yet point a different way for each of them? The answer is that down is not a direction in space. Down is a direction toward a thing. Specifically, down is the direction toward the center of mass of the nearest large enough body, the direction gravity is pulling you, and since you are standing on a ball, that direction points at the middle of the ball, no matter where on its surface you happen to be. For the person in the north, the middle of the earth is beneath their feet in one direction. For the person in the south, the middle of the earth is beneath their feet in a different direction. Both of them are being pulled toward the same point, the center of the planet. But because they are standing at different places on the sphere, that single shared point lies in a different direction for each of them. Down is not one arrow pointing one way through the cosmos. Down is a million arrows, one for every spot on the surface, all of them aimed inward at the same central point, all of them called by the same name. This is why the ground feels flat and level everywhere you go on a round world, even though the world is curved. Wherever you stand, gravity pulls you straight toward the center, which means straight down relative to you, which means the ground beneath you feels perfectly horizontal because it is at right angles to your personal down. Travel 1,000 kilometers, and the ground there also feels perfectly flat and level, even though it is tilted in the larger picture, relative to where you were, because your down has quietly rotated to keep pointing at the center. You never feel the curve. You cannot feel it. The sphere is the exact shape that hides its own curvature from anyone standing on it, because it is the shape that keeps down pointing at the same central place from every position on the surface. The roundness of the world is not just something you can see from space. It is the invisible reason the floor feels level under your feet at this very moment. Sit with what that means, because it is the quiet turn at the center of this whole story. The floor beneath you is not flat. It is a small arc of an enormous ball curving gently away in every direction, and you are stuck to the outside of that ball. The wall you might be leaning against is not truly parallel to a wall on the other side of the planet. It is tilted relative to it, aimed at a slightly different piece of sky, because it too is built along the local down, which points at the center. Every level floor ever built, every wall ever raised straight and true, every surface, a bubble level ever certified as flat, was aligned not to some universal grid of space, but to the pull toward the center of a particular ball. And the pull, doing all of that, the pull that defines down for you and for everyone, is the same pull that took a molten young world and dragged it into a sphere. You are not merely living on the result of that ancient rounding. You are held to it, oriented by it, defined by it every second in the most ordinary sensation you have. The direction you call down is gravity's signature, written not on some distant planet, but on your own body, right now. Try to actually picture it, right now, wherever you happen to be sitting. If you could see through the floor, through the ground, through the rock, straight down along the line your own weight is pulling you, that line would not stop at the floor below you, or even at the bedrock beneath the building. It would continue straight down for more than 6,300 kilometers, all the way to the center of the Earth, and then keep going, out the other side, and it would emerge on the far side of the planet, pointing up into a completely different sky, among stars that no one on your side of the world can see. The direction you call down, and the direction someone standing on the exact opposite side of the Earth calls down, are the same single line, running through the middle of the planet. Its two ends aimed at opposite parts of the universe. Their up is a piece of your down. When you lie in bed tonight and feel yourself pressed comfortably against the mattress, held there, settled, you are being pulled toward a point more than 6,000 kilometers beneath you, and someone on the other side of the world is being pulled toward that very same point from the opposite direction. Both of you hanging off the outside of the same ball, both of you feeling perfectly, unremarkably upright. Neither of you is upside down, because upside down is not a thing the universe recognizes. There is only toward the center and away from it, and the strangeness does not stop with people. The oceans hang off the sides and the underside of the planet without pouring away into space, held to the curving surface by the same inward pull, their surface everywhere following the level that gravity allows. The air wraps the whole ball in a thin shell, held down all the way around, over the top and under the bottom alike, because there is no real top and no real bottom, only in and out. Everything you have ever thought of as lying flat on the ground is in fact wrapped around a sphere, clinging to the outside of it, oriented by a pull toward a center you will never see. You are not standing on top of the world, you are standing on the outside of it, at one particular spot on an enormous ball, and the only reason it does not feel that way is that gravity has quietly redefined down, just for you, to point at the middle. And so the single most familiar fact in your life turns out to be a local truth, not a universal one. Down is a destination, not a direction. It is wherever the center of the nearest big enough thing happens to be. Step onto the moon, and your down swings to point at the moon's center instead. Drift in the empty space between the stars, far from any world, and down evaporates entirely, because there is no dominant center to fall toward, no ball to be stuck to, no gravity strong enough to tell you which way your feet should go. Down is not woven into space. It is manufactured locally, by mass, at every round world, and handed to whoever is standing there. The roundness we have been chasing is not an abstraction happening far away to planets and stars. It is the thing that built the word down. It is under your feet. It is the reason you are not floating. Once you have felt that, the sky is never quite the same, because you understand that you are living, right now, on the curved outer skin of one of the round things, held there by the very rule we have been trying to explain. But if the rule were the whole story, every world would be a perfect ball, and here the story takes a turn, because no world is, not one, not the Earth, not the Sun, not any planet or star ever measured. Every single one of them falls short of a perfect sphere in the same particular way, leaning away from perfection along one specific axis. Something is quietly ruining the ball on every world at once, and the amount of ruin turns out to be one of the most useful things you can measure about a world. Something is fighting the roundness. That something is spin. Part 6. The spin that breaks the ball. Nothing in space sits still, and in particular, nothing in space refuses to turn. Every planet spins. every star spins. Every moon and asteroid and comet turns on some axis at some rate, because the swirling clouds and colliding rubble they formed from were themselves turning, and that turning motion has nowhere to go. It is a quantity nature keeps, and does not let a body simply discard. So worlds are born spinning, and they keep spinning, and that spin, gentle as it may seem, quietly wages war on the perfect sphere that gravity is trying to maintain. The result is that no rotating world is ever a true ball. Every one of them bulges, just slightly, around its middle. The reason is a competition you can feel in your own body. When something spins, every part of it is trying, at each instant, to fly off in a straight line, and it is only the inward pull toward the center that keeps it moving in a circle instead. You feel this on a fast merry-go-round or in a car taking a sharp turn. The sense of being flung outward, away from the center of the turn. On a spinning world, the material near the equator, the widest part, is moving fastest, because it has the largest circle to travel in each rotation, and so it feels the strongest tendency to fly outward. That outward tendency works directly against gravity's inward pull. Near the poles, on the spin axis, there is almost no such effect, because material there is barely moving in a circle at all, so gravity is slightly opposed at the equator and barely opposed at the poles. The equator, in effect, is held a little less tightly, and so the world bulges outward around its equator and flattens very slightly at its poles. The perfect sphere becomes what is called an oblate spheroid, a ball gently squashed along its spin axis, wider across the middle than from top to bottom. The Earth is exactly such a shape, and the numbers are worth hearing because they are surprisingly large. The Earth's radius, measured to the equator, is about 6,378 kilometers. Its radius measured to the poles is about 6,357 kilometers. The difference is roughly 21 kilometers. The equator bulges out about 21 kilometers farther from the center than the poles do, because the planet turns once a day and the equator is being flung outward. This has a consequence that sounds like a riddle, but is simply the bulge showing itself. The point on Earth's surface that is farthest from the planet's center is not the summit of Mount Everest. It is the peak of a mountain called Chimborazo in Ecuador, which sits almost exactly on the equator. Everest is the highest point measured from sea level, but Chimborazo, riding the equatorial bulge, is lifted farther from the center of the Earth than Everest is by a couple of kilometers. Both statements are true at once. Everest is the tallest measured from the sea, and Chimborazo is the farthest from the middle, and the reason they disagree is spin. Turn up the spin, and the effect grows dramatically. The giant planets rotate far faster than the Earth, despite being enormously larger, and they are made largely of gas and liquid that yields easily, so they bulge much more. Jupiter, which turns once in only about 10 hours, is visibly out of round, flattened by about 1 part in 15, a squashing you can see with a small telescope from your backyard. Saturn is more extreme still. Saturn is the most flattened planet in the solar system, bulging by nearly 1 part in 10. Its equatorial radius is about 60,268 kilometers, while its polar radius is only about 54,364 kilometers, a difference of nearly 6,000 kilometers. Saturn is noticeably egg-shaped, or more precisely pumpkin-shaped, squashed top and bottom, and the reason is simply that it spins fast, and its material cannot resist the outward fling. The rings hide it a little, but the globe inside them is clearly not a true ball. Go to the stars, and the effect can become spectacular. Some stars spin so rapidly that they are flung far out of round. The star Achernar, one of the brightest in the southern sky, rotates so fast that its equatorial diameter is roughly 1.5 times its polar diameter. It is not a ball at all in any casual sense. It is a flattened lens of glowing gas, spun nearly to its limit, its equator racing around so quickly that the star bulges out into an oval. Other bright stars, Regulus, Altair, Vega, are all measurably squashed by their rapid spin. And out in the cold Kuiper belt beyond Neptune sits one of the most extreme examples of all, a dwarf planet called Haumea, which turns once every 3.9 hours, faster than almost anything its size. Haumea has been spun so hard that it is not even an oblate spheroid anymore. It is stretched into a genuine elongated ellipsoid, a shape more like an egg or a flattened football, roughly 2,100 kilometers along its longest axis and only about 1,000 along its shortest. Gravity rounded Haumea, and then its own furious spin stretched much of that roundness back off. Haumea is a world caught in the act of losing the shape gravity gave it. The equatorial bulge is not only a fact for astronomers, it reaches into ordinary life in ways most people never notice. Because the equator sits farther from the center of the Earth, and because the outward fling of the planet's spin is strongest there, you actually weigh very slightly less standing at the equator than you would at the poles, by a few tenths of a percent, a difference far too small to feel, but easy to measure with a sensitive enough scale. Space agencies pay close attention to this. Rockets are launched, wherever geography allows, from sites as near the equator as possible, and they are launched toward the east because the equator is not only bulging but also moving fastest as the planet turns, sweeping around at over 1,600 kilometers per hour. A rocket lifting off there is handed that speed as a free head start, a gift from the very spin that raised the bulge, which is why the great launch sites cluster toward the tropics rather than the poles. The bulge also quietly governs the motion of every satellite. A spacecraft orbiting the Earth is not circling a perfect sphere. It is circling a body with a thickened waist, and that extra ring of mass tugs on its path, slowly swinging the whole orbit around over weeks and months in a way that must be calculated and corrected, or the satellite will drift from where it is meant to be. And every precise map and every navigation signal depends on getting the shape right. The systems that tell you where you are standing on the surface of the planet do not model the Earth as a ball. They model it as an oblate spheroid, with the longer equatorial radius and the shorter polar radius written directly into the mathematics, because a simple ball would be wrong by tens of kilometers and would send every position subtly astray. The shape of the world, the exact size of its bulge, is built into the machinery of launch, navigation, and map-making. We do not merely know that the Earth is squashed by its spin, we rely on it, correct for it, and take advantage of it every single day. The wonderful part of this history is that we understood it before we could ever see it, from mathematics alone. In the 1680s, Isaac Newton, working out the consequences of his new law of gravity, predicted that the Earth could not be a perfect sphere. He reasoned that because the planet spins, it must bulge at the equator and flatten at the poles, exactly the effect we have been describing, and he even estimated by how much. This was a bold claim, and it was not universally believed. A prominent French family of astronomers, the Cassinis, had measurements suggesting the opposite, that the Earth was stretched at the poles, egg-shaped the tall way, rather than the squashed way. The dispute mattered enough that in the 1730s, the French Academy of Sciences sent out two great expeditions to settle it, one far to the north, into Lapland, near the Arctic, and one south, to the region of present-day Ecuador, near the equator. Their task was to measure the precise length of a single degree of latitude in each place, because the way that length changes between the equator and the pole reveals the planet's true shape. The expeditions endured years of brutal hardship, mountains and cold and disease and delay, and when their measurements came back and were compared, the verdict was clear. The degree was longer near the pole, which is the signature of a planet flattened at the poles and bulging at the equator. Newton was right. The Earth is an oblate spheroid, squashed by its own spin, exactly as the mathematics had said, and human beings had proven it by walking to the ends of the Earth with measuring instruments before a single person had ever left the ground to look. So the perfect ball is a fiction everywhere. Every spinning world is a compromise between two forces, gravity pulling it toward a sphere and spin flinging its equator outward. And the shape you actually get is the truce between them, an oblate spheroid whose exact degree of flattening tells you how fast it spins and how readily its material yields. Read the bulge and you read the spin. The shape is a measurement. And this idea that the precise way a world departs from a perfect sphere is a reliable, readable record of its physics is about to pay off in the most dramatic way possible, because it leads us to a single object, the largest and most familiar object in the entire sky, which is round to a degree that almost defies belief. To find the roundest thing you will ever meet, we only have to look at the one thing in the sky you were always told not to look at directly. Part 7. The roundest thing you will ever meet. The sun is a furnace. It is a churning, roaring, violent ball of plasma, more than 1 million kilometers across, with a surface that boils and heaves in cells the size of continents, that flings arcs of superheated gas hundreds of thousands of kilometers into space, that shudders with magnetic storms and erupts in flares that could swallow the Earth whole. It rotates, dragging its equator around once in roughly 25 days. By every expectation we have built up so far, it should be flattened, distorted, unruly. It is the most turbulent object in your sky by an enormous margin. And it is, by careful measurement, the roundest natural object anyone has ever found. This is one of the most beautiful facts in all of physics, and it takes a moment to appreciate just how extreme it is. Consider what floating above the sun would actually be like. Below you, in every direction, stretches a surface of blinding, seething fire, granulated into a shifting mosaic of bright cells and dark lanes. Each cell a fountain of plasma, rising, spreading, and sinking back down. It is chaos, on a scale that beggars the imagination, hot enough to tear atoms apart, restless in a way nothing on Earth is ever restless. And yet, when you lift your gaze to the edge of that immense globe, to the curve of the horizon where the blazing surface meets the black of space, that curve is perfect. It is smooth beyond any smoothness you have ever seen. If you could measure the whole globe, you would find that the distance across its equator exceeds the distance from pole to pole by only about 10 kilometers, out of a total width of nearly 1,400,000 kilometers. The most violent object you will ever meet is also, in its overall figure, the roundest thing you will ever meet. Hold that contradiction in your mind for a moment, because it is telling you something profound about gravity. Let the numbers land properly, because they are almost hard to believe. The sun's oblateness, the amount by which it departs from a perfect sphere, is about 9 parts in 1,000,000. To put that in human terms, imagine shrinking the sun down to the size of a beach ball, about 1 meter across. On that scale, the difference between the widest way across and the narrowest way across, the entire bulge, the whole departure from a perfect sphere, would be thinner than a single human hair. You could run your hand over the model and never feel the flaw. A beach ball made in a factory, with all our precision and care, would almost certainly be less round than that. The sun, a ball of fire 1,000,000 kilometers wide with no manufacturer and no quality control, holds itself to a roundness that would embarrass our best engineering. That is what gravity does when it has an enormous amount of mass to work with. The more mass a body has, the more overwhelmingly gravity dominates over every other force acting on it. And the sun has so much mass, about 1/3 of 1,000,000 times the mass of the Earth, that its gravity crushes it toward a perfect sphere, with a force that its own violent churning and its own spin can barely dent. There is a reason this fact lands with such force once you sit with it, and it is worth naming before we move on. Everywhere else in this story so far, roundness and calm seem to travel together. The small, cold, quiet potatoes were the irregular ones, and the smoother a world became, the more settled and finished it seemed. The sun shatters that intuition completely. Here is the most violent, most turbulent, most restless object for light years in any direction, a body that is quite literally exploding without pause, holding itself together against its own fury, only by the crush of its own weight, and it is rounder than a marble from a factory. The lesson is that roundness was never about calm at all. It was always about mass. Calm had nothing to do with it. The sun is round for the very same reason a neutron star is round and a small asteroid is not, because it has so much material that gravity's pull toward the center overwhelms absolutely everything else the object is doing, however wild that everything else may be. The storms on the sun's surface, the flares, the churning cells of plasma, the eruptions of magnetized gas, are enormous by any human measure, but set against the crushing authority of 1/3 of a million Earth masses of gravity, they are ripples on the face of a mountain, powerless to shift the overall shape by more than a whisper, and that near-perfect roundness turns out to matter for physics far beyond the sun itself. The precise size of the sun's tiny bulge changes ever so slightly how its gravity reaches across the solar system, and, in particular, how it tugs on the orbit of Mercury, the closest planet. More than a century ago, some scientists wondered whether a larger-than-expected solar bulge might explain a famous stubborn wobble in Mercury's orbit that Newton's gravity alone could not account for. The wobble turned out to be explained instead by Einstein's new theory of gravity, one of its first great triumphs, and the sun's bulge was later measured to be far too small to be the cause. But the episode shows how much can ride on a shape. The roundness of the sun is not only a beautiful fact, it is a number that had to be pinned down before we could be certain we understood gravity itself. Measuring this was not easy, and the story of how we know is a small triumph of patience. From the ground, the sun's shimmering, the blurring of its edge by the Earth's own turbulent atmosphere, swamps a signal as tiny as a 10-kilometer bulge on a 1,000,000-kilometer disk. You cannot see something that subtle through the churning air, so the measurement had to be made from space. Using instruments aboard spacecraft built to watch the sun, including a mission called RHESSI and the Solar Dynamics Observatory, astronomers were finally able, in the years around 2012, to pin down the true shape of the sun's edge with extraordinary precision. And what they found was not only that the sun is astonishingly round, but that its roundness is remarkably steady. It barely changes as the sun runs through its 11-year cycle of storms and calm. The shape is stable, fixed, almost stubborn, a nearly perfect ball held in place by the sheer authority of an enormous mass over its own material. There is a subtle wrinkle in the data, a hint that the bulge is a touch larger and steadier than the simplest picture predicts, tied to how the sun rotates far down inside itself, and that wrinkle is a live thread in solar physics. But the headline is simple and staggering. The most powerful object in your sky is also the most perfectly rounded. This is the point in the story where the rule we have been building reveals its real character. Roundness is not a fragile thing that only delicate, quiet objects can achieve. It is the opposite. Roundness is what you get when gravity is strong enough to force it, and the stronger gravity is, the more perfect the roundness becomes, no matter how violent the object is otherwise. A small, cold, peaceful asteroid is a lumpy potato. A giant, raging, storming star is a nearly flawless sphere. The difference between them is not temperament, it is mass. The more mass, the more gravity, the more total the victory over every high place and every irregularity, and the closer the result, creeps toward a perfect ball. The Sun is round precisely because it is huge, and its violence is powerless to stop it. Given enough mass, everything surrenders its shape, and the Sun has enough mass to surrender its shape almost completely. And this points somewhere remarkable. If more mass means more perfect roundness, then the Sun cannot be the end of the story. The Sun is round to 9 parts in a million, but the Sun, for all its size, is not the densest or most gravitationally extreme object in the universe. There are objects out there where gravity is not merely strong, but almost incomprehensibly stronger than at the Sun. Objects where the same rule is pushed to a limit that borders on the absurd. If the Sun's mass makes it rounder than a factory beach ball, what does a far greater concentration of mass do? The answer waits for us at the far end of the scale, among the collapsed remnants of dead stars. But before we go there, we have to deal with the losing side of the contest, the force that gravity is defeating in every one of these worlds. We have spent all this time on gravity, the winner. It is time to give the loser its due, because the strength of ordinary material, the thing gravity has to overcome, sets a limit of its own, and that limit is written into the tallest mountains that can ever exist. Part 8. The mountains physics forbids. We have treated material strength mostly as the thing that loses, the stubbornness that holds small potatoes together until gravity grows big enough to win. But strength does not simply vanish once gravity takes over. On every round world, the two forces go on quietly negotiating forever, and the visible result of that negotiation is the terrain, the mountains and valleys and ridges that ride on top of the great underlying sphere. Roundness sets the overall shape, but strength decides how far the surface is allowed to depart from it in the small, how high a mountain can climb before gravity drags it back down. And it turns out there is a hard ceiling on that height, a maximum mountain, and the number is written by the same contest we have been watching all along. The reason a mountain cannot grow without limit is that a mountain is heavy and its own weight presses down on the rock beneath it. Build a mountain higher and you pile on more weight, and that weight bears down harder and harder on the base. Rock is strong, but it is not infinitely strong. Push on it hard enough and it begins to fail, to crumble, to flow, to spread out sideways under the load like extremely stiff putty over long spans of time. There comes a height at which the rock at the base of a mountain simply cannot support the weight of the mountain above it. At that point, adding more height does not build a taller mountain. It just crushes the base, and the mountain sinks or spreads as fast as you pile it up. That height, where the strength of rock exactly gives out under its own weight, is the tallest a mountain can possibly be on a given world, and it depends directly on the strength of the mountains, gravity. Stronger gravity means the same rock weighs more, which means it crushes its base at a lower height, which means the tallest possible mountain is shorter. Weaker gravity means rock weighs less, so it can pile higher before failing, so the tallest possible mountain is taller. On the Earth, this ceiling sits somewhere around 10 to 15 kilometers. Mount Everest rises about 8.8 kilometers above sea level, and that is close to as tall as a mountain on Earth can get. Push much past that, and the base rock begins to yield, and the mountain cannot be sustained. This is not a coincidence of geology or a limit of erosion alone. It is a fundamental cap set by the strength of rock against Earth's gravity. Now compare Mars. Mars has only about 38% of Earth's surface gravity, which means rock on Mars weighs less than half what it weighs on Earth, which means a Martian mountain can climb far higher before its base gives out. And indeed, Mars is home to Olympus Mons, the tallest known volcano in the solar system, which rises about 22 kilometers above the surrounding plains, roughly 2.5 times the height of Everest. Olympus Mons is not taller because Mars is a more dramatic world. It is taller because Mars pulls on its rock more gently, and gentler gravity permits a higher pile before the rock at the bottom fails. The tallest mountain on a world is a readout of that world's gravity. Read the maximum height, and you have measured the pull. This is the same rule as the roundness rule, seen from the other side. A world is round because gravity flattens its large-scale departures from a sphere. A world's mountains are limited in height because gravity crushes its small-scale departures from a sphere once they get too tall. Both are gravity enforcing the sphere. The overall globe is the sphere gravity has already achieved. The maximum mountain height is the leash gravity keeps on how far anything is allowed to stick up from that globe. On a more massive world, with stronger gravity, the leash is shorter, the mountains are lower, and the surface hugs the underlying sphere more closely. On a smaller world, the leash is longer, and the terrain can be wilder. The bigger the world, the smoother it is forced to be, at every scale at once, from its overall figure right down to its individual peaks. The way this ceiling works is worth seeing a little more closely, because it connects straight back to the floating, balancing behavior we met earlier. A mountain does not simply rest on the surface like a book on a table. It presses down into the yielding material below, and is held up partly by buoyancy, floating with a root beneath it. As you build the mountain higher, its root sinks lower, and the rock at depth, under the enormous pressure of all that weight, begins to behave less like a solid and more like something that can slowly flow. Past a certain height, the base can no longer hold. The mountain spreads outward under its own weight, slumping sideways almost as fast as it rises, and it simply cannot get any taller. This is exactly what we see in Olympus Mons, the giant volcano on Mars. It is not a steep, narrow spire. It is a broad, gently sloping dome, far wider than it is tall, precisely because its own weight has forced it to spread across the surface rather than pile up. Mars let it grow to about 22 kilometers, partly because Martian gravity is weak, and partly because Mars, unlike the Earth, does not shuffle its outer shell around, so a single volcano could sit over one hot spot and build for an immense stretch of time. Even there, though, the spreading, the flattening under its own weight, is plain to see, the same rule setting the same kind of limit. And here is the connection back to the whole-scale story. On a small world, a single mountain can be a large fraction of the entire body, which is exactly why small worlds look so lumpy, their few big features standing tall against their modest size. On a large world, the tallest possible mountain is only a tiny fraction of the whole globe, a faint wrinkle on an enormous sphere. The Earth's highest peak rises less than 9 kilometers above the sea, on a planet more than 6,300 kilometers in radius, which makes the mountain barely 1,000th of the way to the center. The bigger the world, the smaller its roughness is compared to its size, and the more closely it hugs the underlying sphere at every scale at once. Size does not only decide whether a world is round in the large, it decides how smooth the world is allowed to be in the small, how tall its tallest feature can stand against the size of the whole. Gravity smooths a large world twice over, once by rounding its overall figure, and again by clamping down on how far anything is permitted to rise from that figure. Let this settle for a moment, because there is something quietly staggering hidden in it. The tallest mountain that can ever exist on a world is not an open question, not a matter of chance or history or how much rock happened to pile up. It is a fixed number, set in advance by the strength of rock against the pull of gravity. There is a height beyond which no mountain, anywhere, on any world of a given size, is permitted to stand, and that height was determined not by any event but by the laws themselves, before the first mountain ever rose. Reality has a ceiling, and it did not have to be argued for or discovered by trial. It was there from the beginning, waiting, built into the arithmetic of weight and strength. When you look at the tallest mountain on any world and understand that it stands exactly as high as physics will allow and not one bit higher, you are looking at a limit that the universe imposed on itself, silently, without asking anyone. Limits like this are not restrictions placed on the universe from outside. They are woven into what the universe is. The mountain that cannot be built is as real a feature of reality as the mountains that can. So the strength of ordinary rock, the loser in our contest, still leaves its mark everywhere, as the fine texture riding on top of the sphere, as the ceiling on how tall anything can rise. But we have been building, this whole time, toward the place where the contest is not close at all, where gravity does not merely win but wins so completely that strength almost ceases to matter, where the leash on the mountains is pulled so tight that the mountains shrink to nearly nothing. We saw that more mass means more perfect roundness, that the sun beats a factory beach ball. Now we go to the objects where mass is packed so densely that gravity reaches a level the sun never approaches, and we find the roundest objects that exist anywhere in the universe. To meet them, we have to visit the corpses of stars. Part 9. Rounder than round. When a massive star dies, it can leave behind a remnant so dense that it rewrites what the word solid even means. A neutron star is the collapsed core of a star that ran out of fuel and fell in on itself, crushing its material past the point where ordinary atoms can survive. What remains is a ball of matter so compressed that a single sugar cube-sized piece of it would weigh about as much as a mountain, a body more massive than the sun squeezed into a sphere, only about 20 kilometers across, roughly the size of a city. The gravity at the surface of such an object is not a little stronger than at the surface of the Earth. It is something like 100 billion times stronger. And at that unimaginable level of gravity, the rule we have been following all evening reaches its ultimate expression. Neutron stars are the roundest objects in the known universe. Picture, for a moment, standing on one, knowing that in reality the gravity would flatten you into a film thinner than paper in an instant. Set that aside and simply look at the ground. Beneath your feet is a surface smoother than anything human hands have ever made or ever could make. The tallest mountain on a neutron star, the highest that its almost inconceivably strong material can rise, before that 100 billion-fold gravity crushes it flat, is not measured in kilometers or meters. It is measured in millimeters. On a body 20 kilometers across, the entire range of terrain, the difference between the highest point and the lowest, might be less than the thickness of a coin. The whole surface, every part of it, hugs the underlying sphere so closely that the deviations are microscopic on the scale of the star. If you polished a ball bearing in the finest laboratory on Earth, you could not come close to this. The gravity is so overwhelming that it permits essentially no departure from the sphere at all. Here, at last, is the contest we have been watching, gravity against strength, decided by total annihilation. Gravity wins so completely that terrain, in any meaningful sense, ceases to exist. The neutron star is very nearly a perfect mathematical sphere, made real, glowing faintly, spinning in the dark. To feel how far gravity has been pushed on such a body, it helps to sit with the density for a moment, because it is genuinely hard to hold in the mind. A neutron star packs more than the entire mass of the sun into a ball the size of a city. A single teaspoon of its material would weigh, here on Earth, something like 1 billion tons, roughly the weight of a mountain, scooped into a spoon. If you could somehow lift out a piece the size of a sugar cube, that cube would outweigh the entire human race put together. This is matter crushed far past the point where atoms can keep their normal structure, squeezed until the empty space that fills ordinary matter has been wrung almost entirely out of it. And it is that unthinkable density that produces the unthinkable gravity, and the unthinkable gravity that produces the near-perfect roundness. The pull at the surface is so strong that the tallest bump the crust can support is a matter of millimeters. Yet, the crust itself is not entirely silent. It is thought to be a solid shell of extraordinary strength, and now and then it can crack and shift in what astronomers call a starquake, a sudden, tiny rearrangement that can, in the most fiercely magnetized of these stars, loose a flash of radiation clear across the galaxy. Even then, the shape barely changes. The star settles straight back to its almost flawless sphere. Many neutron stars spin, and some spin astonishingly fast, hundreds of times every second, whirling with a regularity so exact that as their beams of radiation sweep past the Earth, like the turning beam of a lighthouse, they arrive with the steadiness of the finest clocks found anywhere in nature. A ball heavier than the sun, only a few kilometers across, turning hundreds of times a second, and holding its roundness to within a hair the entire while. That such an object keeps its shape at all, under forces so extreme, is one of the plainest demonstrations there is of how completely gravity takes over once mass is concentrated enough. There is nowhere for a high place to hide. The pull toward the center is so total that the very notion of terrain, of one place being higher than another, has been all but erased, and that near perfection is not just a curiosity. It is something we actively hunt for, because the tiniest departures from it would tell us things we desperately want to know. A perfectly round, spinning object gives off no gravitational waves, no ripples in the fabric of space, because a perfect sphere spinning looks exactly the same at every moment and space has nothing to ripple about. But a spinning object with even the slightest bump, the smallest deviation from a perfect sphere, would radiate a faint, continuous hum of gravitational waves as it turned over and over forever. So the great gravitational wave observatories, the enormous, exquisitely sensitive detectors that first caught the ripples from colliding black holes, listen patiently for that steady hum from spinning neutron stars in our own galaxy. They have not heard it yet. And the silence itself is a measurement. It tells us that these stars are round to within the tiniest fraction, that their mountains, if they have any at all, are smaller than we can yet detect, that the roundness enforced by their monstrous gravity is very nearly total. We are measuring the perfection of these spheres by the fact that we cannot yet hear their imperfection. Even here, though, the old adversary of spin has not entirely surrendered, and neither has gravity's final form. Push to the most extreme object of all, a black hole, and the rule follows you right up to the edge of what physics can describe. A black hole that is not spinning has an event horizon, the boundary of no return around it. That is a mathematically perfect sphere, the purest sphere in all of nature, a surface defined by gravity alone, with no material to be lumpy or strong or weak. It is roundness in its most absolute form, gravity making a shape out of nothing but the geometry of space itself. But set that black hole spinning, and even it bulges. A rotating black hole's horizon flattens at its poles and swells at its equator. An oblate spheroid, drawn in the fabric of space-time, the very same squashing we saw on the spinning Earth and the spinning Sun and the spinning Saturn, reappearing at the most extreme gravity that exists. The identical compromise, gravity pulling toward the sphere and spin flinging the equator outward, plays out on a city-sized dead star, on a giant planet, on a raging sun, and on the warped boundary of a black hole. It is the same negotiation everywhere, at every scale, from the potato to the horizon of a black hole. Only the strength of the two contestants changes. The contest never does. Step back and look at the whole ladder we have climbed. At the bottom, the small, cold potatoes, where the rock is strong and gravity is faint, and the shape is whatever it happened to be. A little higher, worlds like Mimas, sitting right on the threshold, just barely rounded. Higher still, the Earth, comfortably round, but bulged by its spin, its tallest mountains reaching their permitted ceiling. Higher again the Sun, so massive that it is round to within a hair on a beach ball despite all its fury. And at the very top, the neutron stars and the black hole horizons, where gravity is so overwhelming that roundness becomes almost geometrically perfect, terrain shrinks to millimeters or vanishes into pure space-time, and the sphere is realized as nearly exactly as the universe ever realizes anything. It is a single rule, playing out across an almost absurd range of sizes and intensities, from a comet you could walk across in an afternoon to the crushed corpse of a star. The more mass, the more gravity, the more perfectly round. The rule does not change, only how completely it wins. We have now followed the rule all the way to its limit, and it has held at every step. But a good rule is best understood by pressing on the places where it seems to break, on the exceptions and the oddities and the objects that appear, at first glance, to defy it. There are worlds wearing shapes that do not match their present spin. There is the most stubborn fringe belief of our age, the claim that a certain world is not round at all, and there is the largest question of all, the fact that the universe as a whole refuses to be a ball. If we want to be sure we truly understand why everything in space is round, we have to go and examine the things that supposedly are not. Part 10. The shapes that refuse. If the rule is as ironclad as we have been claiming, then the exceptions ought to be the most interesting objects of all, because a rule is tested at its edges. And there are exceptions, or at least there are objects that look at first like exceptions. There are worlds that are round in a way that does not match how they spin today. There is the most persistent claim in modern culture that one particular world is not round at all. Each of these seems, on the surface, to challenge everything we have built, and each of them, when you look closely, turns out to confirm it more deeply than a well-behaved sphere ever could. Start with the strangest of the well-behaved oddities, a moon of Saturn called Iapetus. Iapetus is a world with two faces, one hemisphere dark as coal and the other bright as fresh snow, turning slowly through space with an eeriness that unsettled astronomers for centuries. But its strangest feature is not its colouring, it is a wall. Running almost exactly along the equator of Iapetus is a ridge of mountains, in places over 10 kilometres tall, wrapping around the moon like a seam, as though the world had been cast in two halves in a mould, and no one had filed down the join. And Iapetus has another peculiarity. Its overall shape, its degree of flattening, does not match its present spin. Iapetus turns very slowly today, once in about 79 days. A body spinning that lazily should be very nearly a perfect sphere, because there is almost no outward fling to bulge its equator. But Iapetus is noticeably flattened, squashed as though it were spinning many times faster than it actually does. Its shape is wrong for its rotation. The explanation is beautiful, and it deepens everything we have said. Iapetus is wearing an old shape. Long ago, when it was young and warm and soft, it spun much faster, and while it was soft, gravity and that rapid spin together pulled it into the flattened, bulging shape appropriate to a fast rotation, exactly as our rule demands. But then Iapetus cooled, its material hardened and grew strong before its spin had slowed, and when a body's material becomes strong enough, it can hold a shape against gravity, just like a potato. So as Iapetus gradually slowed over the ages, its frozen, rigid body kept the flattened figure it had locked in during its fast-spinning youth. The shape is a fossil. It is a record of how the moon used to spin, preserved in solid rock long after the spin itself changed. Iapetus does not violate the rule. It obeys it twice. It obeyed gravity when it was soft, taking the shape its spin demanded, and then it obeyed the strength of cold rock, keeping that shape when it could no longer flow. Its wrong-looking shape is not a failure of the rule. It is the rule caught in the act of remembering. A world's shape, it turns out, can be a clock, and some worlds are still wearing the wrong time. Now turn to the exception that people actually argue about, because roundness is the exact point where basic physics collides with the most stubborn fringe claim of our era, the belief that the Earth is flat. It is worth taking the question seriously rather than waving it away, because the physics gives an answer that is far more interesting than mockery, and the answer is the whole lesson of this evening stated as a prohibition. The decisive point is not a photograph from space. The decisive point is that a world with the mass of the Earth cannot be flat and could not stay flat even if some force assembled it that way. We have spent 2 hours establishing why. At the Earth's mass, gravity overwhelms the strength of rock by an enormous margin. That is precisely why the Earth is round in the first place. A flat, disc-shaped Earth with the same mass would have gravity pointing not uniformly downward through the disk, but inward toward the disk's center of mass. The edges of the disk would be pulled toward the middle. The rock could not possibly support that pull, any more than it can support a mountain taller than the permitted ceiling, and the disk would collapse, its rim avalanching inward, folding and slumping toward the center, until it reached the only stable shape available to that much mass, a sphere. The same rule that rounds every large moon and planet and star forbids a large flat one from persisting even for a geological moment. Roundness is not an opinion about the Earth. It is a requirement gravity places on anything with the Earth's mass, the very same requirement we have watched enforce itself on Mimas and on Ceres and on the Sun. It is worth pausing on just how long ago and how cleverly human beings first measured the roundness of the Earth, because it puts the modern doubt in perspective. More than 2,200 years ago, a Greek scholar named Eratosthenes, working in Egypt, not only knew the Earth was a sphere, but measured how large it was, using nothing but shadows and reasoning. He had learned that in one southern city, on a particular day of the year, the noonday sun stood exactly overhead, so that a vertical stick cast no shadow at all, and sunlight reached all the way to the bottom of a well. In another city far to the north, on that same day, and at that same hour, a vertical stick did cast a shadow, because there the sun stood at a slight angle away from straight up. On a flat Earth, the sun's rays would strike both cities at the same angle, and both sticks would behave exactly the same way. The fact that the two cities saw different shadow angles could only mean the ground between them was curved. Eratosthenes measured that angle, found it to be about 1/50th of a full circle, and reasoned that the distance between the two cities must therefore be about 1/50th of the way around the whole planet. He knew that distance, and so, with a single multiplication, he arrived at the circumference of the Earth. His answer, translated into modern units, came out remarkably close to the true value of about 40,000 kilometers, a staggering achievement for a man working with sticks, shadows, and the correct, by then already well established, assumption that the Earth is a ball. The roundness of the world was not a guess, and it was not a modern discovery. It was measured carefully and correctly before the Roman Empire existed. Every serious navigator and astronomer for the next 2,000 years built on that knowledge, because it worked, because it predicted what ships and stars and shadows actually did. And the direct evidence, remarkably, is old, and it never depended on spaceflight. More than 2,000 years ago, Aristotle pointed out that during a lunar eclipse, when the Earth passes between the Sun and the Moon, the shadow the Earth casts on the Moon is always round, no matter the time of night or the season, and only a sphere casts a round shadow from every angle. He noticed that travellers moving north or south saw different stars rise and set, which only makes sense on a curved surface. Ships have always vanished hull first over the horizon, the lower part disappearing before the mast, exactly as they should on a curving world, and not at all as they would on a flat plain. Magellan's expedition sailed continuously in one direction and arrived home. And in the 1730s, as we heard, French expeditions did not merely confirm that the Earth is round, they measured the subtle equatorial bulge and proved the planet is an oblate spheroid, precisely as gravity and spin require. Every one of these proofs predates the first photograph of the Earth from space by centuries. When the astronauts finally did look back and see a blue sphere hanging in the black, they were not discovering the shape of the world. They were confirming what gravity had guaranteed and what careful people had already proven with shadows and stars and measuring chains. A related idea, that the Earth might be a hollow shell with a world inside, fails on the same physics from the other direction, because inside a uniform shell gravity cancels out completely, leaving no down to hold anyone to an inner surface, and a shell that large could not hold itself up against collapse in any case. So the exceptions are not exceptions. Iapetus wears an old shape because cold rock remembers, which is the rule, not a break from it. The Earth cannot be flat because a large mass is forbidden to be, which is the rule stated as a law against its opposite. A potato is just a world that never grew big enough to lose the fight, and a fossil-shaped moon and a supposedly flat planet are simply the same contest between gravity and strength, read at different sizes and different moments in time. Every place the rules seemed to break, it turned out to hold, and to hold more revealingly than it does in the simple cases. But there is one last apparent exception, and this one is real, and it is the biggest one of all. Because we have been saying all evening that gravity rounds everything given enough mass, and the universe as a whole contains more mass than anything. So why is the universe not a ball? Part 11. Everything surrenders its shape. We opened with a question so ordinary that no one asks it, and we can now see how far down it goes. Why is everything in space round? Because gravity pulls every part of a body toward its center, and given enough mass, that pull overwhelms the strength of whatever the body is made of, and drags it into the one shape, with no high places left, the sphere. We have watched that single rule govern an almost unbelievable range of objects. The lumpy potato asteroids, where gravity is too weak to win, the moons sitting right on the threshold, just barely rounded. The molten young worlds pulling themselves into balls and freezing that shape forever. The spinning planets bulging at their equators, the Earth lifted highest, not at Everest, but at Chimborazo, on its swollen waist. The sun, round to within a hair on a beach ball despite its fury. The neutron stars, rounder than anything human hands could machine, their mountains shrunk to millimeters. The same rule every time, only more or less complete, depending on how much mass gravity had to work with. A sphere is what gravity builds when nothing is left to stop it, and across all of those objects, at their various sizes, nothing was strong enough to stop it for long. But now hold the whole universe in your mind, the largest scale there is, and the pattern breaks. Zoom out, past the planets, past the stars, past the galaxies, each holding hundreds of billions of stars, out to the grandest structures that exist, and the roundness is gone. Galaxies are not balls. Most of them are flattened disks, wide and thin, because they spin, the same spin that squashes a planet drawn out to its ultimate conclusion. And the galaxies themselves are not scattered evenly, nor gathered into some great cosmic sphere. They are strung along immense filaments, threads of galaxies stretching across hundreds of millions of light years, wrapped around enormous empty voids, joined at great knots and clusters, the whole arrangement looking less like a collection of balls and more like a web or a network of foam or the branching of some titanic root system. The largest structures in the universe are not spheres at all. At the biggest scale, gravity, the great maker of balls, makes threads and walls and emptiness instead. The rule that shaped every world so faithfully seems, at the largest scale, to have abandoned the sphere entirely. The reason reveals what roundness really is, and it returns us to that word we redefined in the middle of all this. Down, we said, is not a direction in space. Down is a destination. It is the direction toward the center of the nearest large enough thing, and it exists only because there is a single dominant center to fall toward. A planet has such a center. A star has such a center. That is why they are round, because every part of them has one clear place to fall, and they all fall toward it until the sphere is complete. But the universe as a whole has no center. There is no single point that all the matter in the cosmos is falling toward, no one place that serves as down for everything. Instead, there are countless centers, every clump of matter pulling on its neighbors, and layered over all of it is the expansion of space itself, stretching the whole arrangement apart even as gravity tries to draw it together. With no single center to fall toward, and with space expanding between the clumps, matter does not collapse into one great ball. It collapses locally into countless separate balls, the planets and the stars, while on the largest scale it is pulled into the stretched, tangled web we actually see. Roundness, then, is a local phenomenon. It is what gravity does when there is a clear center to fall toward. In the middle band of sizes, where gravity is strong enough to beat material strength, but the object is small enough to have one center and to sit below the stretching reach of cosmic expansion. Above that band, there is no single down, and so there is no ball. And this is where the ordinary question we started with quietly opens onto something physics has still not finished. The same force that so patiently and reliably rounds off every world is the force we understand least at the very largest and very smallest scales. On the largest scale, the web of galaxies is shaped by gravity working together with things we have named but not fully explained, the unseen mass we call dark matter that provides much of the pull, and the stretching we call dark energy that drives the expansion apart, and both of those remain among the greatest open questions in all of science. On the smallest scale, gravity refuses to fit together with the quantum rules that govern everything else, and reconciling the force that makes the stars round with the physics of the very small is the great unfinished work that has occupied physicists for a century. So the roundness of a world, the most ordinary sight in the sky, sits on top of a force we have measured exquisitely and still do not fully understand. The perfect ball of a star and the unround web of the cosmos are two faces of the same force, and the fact that we can predict the first to a hair while still arguing about the second is a fair summary of where our understanding stands. It is worth lingering on that cosmic web for a moment, because it is one of the most beautiful and least appreciated facts about the universe, and it completes the picture of what roundness is and is not. When astronomers map the positions of millions of galaxies across the reachable universe, they do not find them sprinkled evenly, like sand shaken across a table, and they do not find them gathered into one great central ball. They find them arranged in a pattern that looks uncannily like a network of threads, or the foam of countless soap bubbles pressed together, or the branching of some enormous root system. Galaxies string together into long, glowing filaments hundreds of millions of light-years in length. Those filaments meet at dense knots, the great clusters of galaxies, and between them open immense, nearly empty voids, bubbles of near-nothingness so large that light takes hundreds of millions of years to cross a single one. This is the largest scale structure there is, and it is the exact opposite of a smooth ball. Gravity built it, the very same gravity that rounds the planets. But here gravity was working with no single center to pull toward, and while space itself was stretching everything apart, and so instead of one clean sphere, it wove a tangled web. What we are seeing, when we set the perfect roundness of a star beside the ragged web of the cosmos, is one force behaving in two completely different ways depending on the scale it is working at. And the reasons it behaves so differently are tied to the two greatest unsolved problems in physics. On the largest scales, the web is shaped not only by the matter we can see, but by the far greater quantity of unseen matter we call dark matter, whose gravity provides most of the scaffolding the galaxies hang upon, and whose true nature no one has yet identified. And the voids go on widening, the whole web being pulled apart faster and faster by the stretching we call dark energy, which makes up most of the universe and which we understand even less. Meanwhile, at the opposite end of the ladder, gravity stubbornly refuses to fit together with the rules that govern the very small, the quantum rules that describe every other force with astonishing precision. Reconciling the force that rounds the stars with the physics of atoms and particles is the great unfinished labor that has occupied physicists for a full century and remains undone. So the humble roundness of a world sits atop a force we can measure to exquisite precision and still cannot fully explain. We can predict the shape of a planet to within a hair, and we cannot yet say what most of the universe's gravity actually comes from, or how gravity works at its very deepest level. So the next time you see the moon, round and low on the horizon, or watch the sun go down, or look at a photograph of a planet hanging in the black, you might let the ordinary question surface for just a moment and feel how much is folded inside it. That shape is not decoration, it is a confession. It is a world telling you that its own gravity grew strong enough to defeat the strength of its own rock, that it fell inward on itself until there was nowhere lower left to fall, that it surrendered its shape because, given enough mass, everything does. It is telling you that down, the most solid direction in your life, is not a direction at all, but a destination, the pull toward a center you are standing on the outside of right now. And it is telling you, in the same quiet breath, that the force writing that perfect curve is the same force whose largest and smallest behavior we still cannot fully explain, that the ball in the sky is not a settled fact, but an open clue, a piece of a puzzle we are still, after all these centuries, in the middle of reading. The most familiar shape in the universe turns out to be one of its unfinished sentences. And it has been hanging over your head, in plain sight, your entire life, waiting for you to ask why.